Well, hello, everybody. Let's see how we're doing for time here. About one more minute. While we're waiting, let's see, it looks like we got 30 participants. That's good, but we should have more than that. How's everybody doing? And anybody do anything fun over the weekend, or did you all stay at home like you're supposed to?
Stayed home.
Yeah, doing Gucci, pet the cat. Okay, let's see. Oh, by the way, I am recording this, so be careful what you say. Okay, well, my clock says it's 1. Let's go ahead and get started. Let me, okay. All right, so here are the answers. Well, actually, before we do that, let's go back here. Does anybody have any questions, not about the homework, just questions about how the class is run or anything in general? I will go over the homework in just a sec, but first I want to see, does anybody have any questions? Lots of no's. Okay, well, let's jump right into the homework then. All right, so as usual, here are the answers to the ones that you haven't already looked up. So I'll give you a little time to look at those. So does anybody have any questions about how I got any of those? Number 12.
I thought if something was neutrally charged that it wouldn't be attracted at all.
Ah, thank you for reminding me about that. I definitely want to talk about that. And in fact, let's go over that right now. I see that Yasin's asking about number 12, and I'm glad to see that because I was planning to go over number 12, even if nobody had asked. But first, I want to talk about Jaren's question because that's really, really important. And in fact, I should have prepared a slide for it, but I didn't. So let me go to a new slide here. Just okay. Gonna have to, let's get rid of those. Okay, so let's create some shape here. This is an object that is neutrally charged. And so let's get some other shape here. Okay, and so let's say that is something that is positively charged. Or it could be negative, doesn't matter. Okay. And let's give it a whole bunch of charges. Okay. So this ball here is neutrally charged. And yet, as they say in the book, this neutrally charged object will get attracted to the rod, which Jaren is correctly saying, wait a minute, at first glance, that doesn't make sense. But the key is charging by induction. Okay, so let's copy one of these over here. Okay, and let's put a bunch of them there. Okay. So here's this neutrally charged thing. It's got a bunch of plus charges, but it is neutrally charged, right? So that means for every plus charge that it's also got a minus charge. So let's get a couple of those. Okay, that looked, we got equal numbers now, pluses and minuses. And let's put the pluses and the minuses close to each other here. Okay. So we have this object that started out, well, in fact, it is neutrally charged, but when we bring this positively charged rod next to it, what's going to happen? Remember charging by induction. Okay, what's going to happen is that the minus charges are going to be attracted to it. So let's get them over on the right side here. The positive, oops, that's a minus charge, got the wrong one. Okay. Okay. Hard to grab the thing that I want to grab there. Okay. All right. So when we bring this plus this positively charged rod next to it, the minus charges, they all move over close as they can get. The plus charges, they all move as far away as they can get. It's still neutrally charged, but here's the key. What's the equation for the force? It's equal to K times Q1 times Q2, and all divided by, whoops, R squared, right? Let me put it up there. All right, so if this is the equation, notice down on the bottom here, the R squared, that's the important thing. So these negative charges, they have all moved over closer to the rod. The plus charges have moved farther away. So R for the negative charges is smaller than R for the positive charges. So even though the Q1 and Q2 is the same for the positive and negatives, the R is different for the positives and the negatives. So these negative charges, because they're closer, they are going to feel a stronger attractive force than the positive charges will feel negative charges. And so what's going to happen is this thing is going to get sucked right in, okay, until it touches the rod. Now, when it touches the rod, then things get interesting. Depends on whether it's a conductor or an insulator. But does that answer your question, Jaron? That's the reason why these negatively charged little objects actually, or I'm sorry, these neutrally charged little objects actually do get attracted. Does that answer your question, Jaron?
Yes.
Okay, good. And that's, I'm glad you reminded me because I definitely wanted to talk about that. Okay, so Yasin was asking about number 12, and I'm glad he did because I was going to do it even if nobody had asked. All right, so problem number 12, I take the words that they used and I put them into a picture, and here's what I get. So sphere A is at the origin, sphere B is 0.6 meters to the right of it, and sphere C is 0.8 meters to the right of it. Right, so what I want to do is I need to figure out what is the charges on sphere A. Now, here is the important thing. I don't remember if I used this term last time or not. The principle of superposition. I don't remember if I used that or not, but that is really, really important. This is something we're going to be using a lot here. What the principle of superposition says is that if you have multiple objects, just take them two at a time. So you can see what I've done on this slide right here is I've grayed out sphere C. So I'm pretending like sphere C isn't even there at all, pretending that the only objects in the world are sphere A and sphere B. All right, so then I can, in fact, let me go back to full screen mode here, if it'll let me. Okay. All right, so I'm back in full screen mode. Okay, so those are the only two objects in the world as far as I'm concerned about right now. Okay, so then I use Coulomb's law, and I can calculate what the force on each of these objects is. And so I get, if I do the math right here, I get that the force is 0.18 newtons. And remember that this is the force on both of them. That means that sphere A is feeling a force of 0.18 newtons pulling it towards sphere B, and sphere B is feeling the exact same force but in the opposite direction. Remember Newton's third law, okay? And so that's the situation. Okay, so Yasin is asking, why is it not negative? It is. Oh, you're asking why didn't I put a negative sign here? Oh, okay. All right, so thank you for asking. That's a good question, important question. So what I like to do when I'm using Coulomb's law is I just work with absolute values, and I let the picture tell me what direction. Because remember, the minus sign, all that tells you is the direction, right? Okay, so what I like to do is I like to let the picture tell me the direction. Now, if you wanted to, you could be really careful and put in the minus and let that work. But I prefer my way. If you would rather do it differently, that's fine. So I work with absolute values, and then I look at the picture and let the picture tell me the direction. Okay, so I get this as the force that's on sphere A due to sphere B. Right now, we need to go back because it turns out that sphere B is not the only thing in the universe. We also have sphere C. But again, I'm using the principle of superposition, which means that you see how I've grayed out sphere B, so I'm kind of temporarily pretending it's not there. So now the only thing in the universe is A and C, and they both have the same charge. So I know ahead of time that the force is going to be repulsive. So again, just working with the absolute value, so I get the direction from the picture. And so now I just want to know the absolute value of the force, the magnitude of the force. All right, so again, I put in the numbers, and I get 0.1125 newtons. And so that's the sphere on A due to C, but it's also that's the force, sorry, on A due to C, but that's also the force on C due to A, again, equal and opposite. Okay, so now I've taken care of all the pairs. So now I have to focus in just on sphere A all by itself. So those are the two forces that are acting on sphere A. So I've got 0.1125 to the left, 0.18 to the right, add them up, and I get 0.068 newtons to the right. So Yasin, does that answer your question? Or anybody else? I'll pause while you type in something. Okay, good. All right. Now, when I made the homework assignment, I was in kind of a hurry. And I looked at problem number 12. And like I say, I was in a hurry. And I thought that it was a I thought that it was a two-dimensional problem. And then later, when I worked through the answer, I saw it was only a one-dimensional problem. And I was really bummed out that none of the homework problems were two-dimensional problems, because you need to know how to do two-dimensional problems. And so I'm going to give you a problem right now.
No, there was a two-dimensional problem, but it technically just involved replacing a number with another one from the practice.
Yeah. Okay. So I'm gonna take problem number 12 and I'm gonna modify it, and I want you guys to do it. But before I do that, I see Maddie has asked a question. What if you have an object that's not attracted to either positive or negative? If I understand the question right, you can just ignore it. But I'm not sure I'm understanding your question right. So, because now, maybe what you're thinking is that you've got a large sphere that becomes charged by induction, like we were talking about earlier when we were answering Karen's question. So we are assuming that these spheres are all really tiny spheres, so that charging by induction doesn't really matter. Okay, so Josh is suggesting, what if we did problem number 12 as if it was two-dimensional? So Josh, you get the prize for reading my mind, because that is exactly what I want to do right now. Okay, so I'm going to take problem number 12 and I'm going to change it so that it's the same numbers as before, the same distances, but I'm going to take sphere B and I'm going to move it so it's up above. Okay, and so now I want you to do this problem like this. And let's see, should I sit and wait while you guys do it? It's probably not the best use of our time for us to sit and wait. If this was a real class, I would do that. I would say, okay, guys, get to working on it. But since this is an online class, did I say real class? This is a real class. You know what I meant. Okay, so rather than me sitting and waiting while you guys work on it, let's do it together. So this is problem number 12, but it's revised. Okay, so let's go through it and see how it works. Okay, so again, we're going to use the principle of superposition. We're going to pretend the sphere C isn't there. We're only going to work with A and B. And since it's the same numbers, the same distance, same charge, same everything, the only thing that's different now is the direction. So I'm going to get, so when I do the numbers, I'm going to get that exact same 0.18 newtons that I got before, except this time the direction is upwards, whereas before it was to the right. Okay, all right, and so now I know that force. Now again, you use the principle of superposition. This time I've grayed out sphere B, so the only thing in the things in the universe are A and C. And again, it's the same numbers and same distances, so I'm going to get the exact same force, okay? But now these two forces are not opposing each other. One is up and one is to the side, okay? But that's not a problem. You guys know how to add vectors, right? You're all experts at adding vectors. So if I've got sphere A and it's got these two forces acting on it, all I have to do is add up the vectors and we're done, okay? And so now let me back up here. So this picture that you see right now, this is the best way to represent what's actually happening to sphere A. It has two forces acting on it, and this picture that you see right here, that is the best way to illustrate what's happening to it. But when it comes time to add the vectors, I do not want to draw them that way. I'm going to draw them the way that a sailor would draw them. Remember, we talked a lot about that. Sailors don't know how to do math. They don't know trig, but they do know how to add vectors, and they can do it on graph paper. So all they do is they get out a piece of paper, piece of graph paper, and they draw the one vector, being very careful to make sure that the length of this arrow corresponds to the magnitude. And then where the first vector ended, that's where they start drawing the second vector. And again, they make great care to be sure that the length of that vector is represented by the magnitude. Okay, and then what they do is they draw the hypotenuse. Now we can use Pythagorean theorem to figure out exactly what the hypotenuse is, but a sailor would just get out a ruler and just measure it. Okay, all right, so the answer then is going to be 0.21 newtons. And then as far as the direction goes, well, if you were a sailor and if you had done it on graph paper very carefully, just get out a protractor and measure the angle. And that's good enough for sailors, but that's not good enough for you because you guys know trig. And so you do the inverse tangent and voila, you get the angle there, so 58 degrees. So even though you didn't have a problem like this on the homework, I guarantee you will have a problem like this on the test. So make sure you are good at doing these types of problems. All right, so Ellie is asking a question. Let me bring the window. I have so many things on my window here, it's kind of hard to see. Okay, so Ellie wants to know how I got the directions of the vectors. Okay, all right, so let's back up here. Okay, so the original problem was this, all right? So just looking at the picture, I know A and C, they're both positive, right? So I know just looking at the picture that the force on A is going to be to the left. It's going to be away, because remember, like charges repel, opposite charges attract. So just looking at the picture, I know that the force on A is going to be to the left. And A and B, they're opposite charges, and opposite charges attract. So that tells me that the force on A is going to be upward. So that's, okay, so there's what you see there is the force due to B, which is upward. There's the force due to C, which is to the left. Add them together, bingo, I get that. That answer your question, Ellie? While you're typing in your answer here. So Yasin wants to know how we would write the units of degrees, such as north or west. Okay. So Yasin, the answer to your question is, well, we don't really have a north, south, east, west in this case. So you just have to draw the picture and label the angle. That's probably the best way to do it. Okay. So everybody good with that? If I don't see any objections, I'm going to move on. Oops. Okay. Okay. All right. Now, some of you have looked at the extra credit assignment that I told you that you could do for extra credit. But really only a few of you. Most of you have not done this assignment. And it's extra credit, so okay, fine. No harm if you don't.
It
But
says
let
that it
me,
was due April 3rd.
can you say that again?
It said it was due April 3rd.
Right, yeah, I understand that. Okay. So I am going to give you until Friday to do it, but once Friday is over, I won't give you any credit for it if you don't do it. So get it done. And it's really important you guys understand, even though this is not covered in the book, I think it's extremely important. So I guarantee you that there will be a question on our next test where you're going to have to know this material. So I highly recommend that you do the extra credit problem. But hey, if you think you understand it, then fine. Tell you what I'm going to do right now is I'm just going to very, very briefly go over it again, just because I do think it's so important. So the incredibly useful thing about semiconductors is that they can temporarily become conductors. And then once you're done with that, you can have them go back to being an insulator again. That is a tremendously useful thing. And the way that it's useful, okay, let's build ourselves a DRAM again. So remember, a DRAM is just a memory cell in a computer. So what we're going to talk about is a bit. So this is where we store a 1 or a 0. So we start with silicon, we drill a hole in it, and we put some metal in there. So that's what we're going to call a capacitor. And by the way, we're going to talk a lot more about capacitors maybe next time or maybe the time after that. We're going to learn a lot about capacitors. But basically, a capacitor is just a thing where you can store charge. All right, so that's where we want to store the charge. Okay, and so what we've done is we've purposely introduced some impurities into the silicon. You can think of it as if we have a gun that's super, super accurate, and we are taking little molecules of anything that's not silicon, but it turns out that phosphorus and boron work the best. Okay, and so we're shooting these into the silicon. So these regions that you see in blue here, those now, they have impurities in them. And now, remember how I said you can make it temporarily be a conductor? Well, this way is not a temporary thing. Once those impurities get in there, you can't get them out again. So these two blue regions, they are now permanently conductors, and you cannot undo that. Okay, so let's give a name to those blue regions. Let's call them the implant wells. Okay, it's a well because it's down below the surface, and an implant is because we have implanted some impurities into there. All right, so now we're going to put a little piece of glass on top of the region in between them. We're going to call that piece of glass the gate insulator. We're going to put a conductor on top of that. It doesn't have to be metal. I mean, it's easiest to think of it if it's metal, but to be honest, nowadays they don't use metal. They use other things. But back in the old days, they used metal. But as long as it's conductive, that's all we care about. And then we're gonna blanket everything with a layer of oxide. Oxide is another word for glass, because silicon dioxide that's glass. That's what it is. Okay, so it's all covered with this nice blanket to keep everything inside. All right. So, and then the one thing is the region in between the two implant wells directly underneath the gate. That's called the channel, because that's where the current is going to flow once we're ready for it to flow. All right, so if we drill little holes through the oxide blanket layer so that we can connect some wires, okay? If we close that lower switch, the charge comes into the implant well on the left, but it cannot get through to the capacitor because the gate is closed. The channel is not a channel right now. All right, so if we want to make it open the gate so it can flow, what we do is we close the switch on the top so the charge can come into the gate. The charge cannot get through the insulator, but charging by induction takes place. All those plus charges that you see up there, those cause the negative charges to get pulled up toward the top, the positive charges get repelled. So all those excess of electrons that wouldn't normally be there, but now we've got more electrons than normal, so they act like impurities, and so they make that channel region become conductive. But the important thing is that it's only temporarily conductive. But right now it is conductive. Okay, so now when we close the lower switch, the charge can flow through into the capacitor. So the capacitor builds up. Okay, We then open the switch on the top and then allow all that charge to dissipate. So we've closed the gate and we have trapped the charge in there, and we have just stored a digital 1. Now, if we want to store a digital 0, that's okay. We close the gate, and this wire over here that was previously connected to the battery, we connect it to what's called ground, which is just kind of a place where it can absorb all the electrons. Will these slides be posted separate from the Zoom video on Canvas? No, I wasn't planning on doing that. If you want to see these slides, just look on the Zoom video. That should be good enough. Okay, so anyway, so we've opened the gate, we've connected over here to ground, so all of the charges can now escape. And now we want to lock it so that the charges stay out. So no problem, we just open up the gate again. And so what we've done now is we've stored a digital 0. Okay, so if you want to store a photograph or music or whatever else on your phone, what you need to have billions and billions of these, and I do mean literally billions. And so you might wonder, how in the world can you get billions of these things on a little tiny chip that's no bigger than the size of your fingernail? Well, that's the magic. That's what I spent my career doing back before I retired. Was figuring out how to jam billions and billions onto a little sliver no bigger than the size of your little fingernail. It was fun. I really, really enjoyed doing that. And it worked out pretty well for me. I was able to retire when I was still only 45 years old. Okay, so that's it for semiconductors. If you understand what I just went through, then that's what you need for the test. There's not really any calculations. I do need to warn you that what I've just shown you is a gross oversimplification. If any of you ever go to work for a semiconductor company like Micron, who, by the way, has a big factory down in Lehi, Utah, where they make semiconductor memory, if any of you get a job down there, you're going to find out that what they do down there is slightly different from what I've described here. But I don't want to go into details right now. Sometimes simplifying is good, and this is one of those times. Okay, so I'm going to move on now, unless I see any objections in the comment screen. Okay, so I hope that some of you have noticed the similarity between Coulomb's law and Newton's law of universal gravitation. You see that with Newton's law of universal gravitation, the force was proportional to the m1, m2, and inversely proportional to r squared, and the proportionality constant was the number that we call g. Well, for Coulomb, it's the exact same form. It's proportional to Q1, Q2 over R squared, and the proportionality constant, it's a different number, but the form is exactly the same, okay? Isn't it interesting that they look so very, very similar? Well, there's a reason why they look so similar. It's because what's happening to physics here. So remember how I keep saying empty space isn't empty. When I graded your test, I noticed that some of you, when you wrote the answer, some of you apparently think that when I say that empty space isn't empty, some of you think that what I mean is that it's not a total vacuum. You're saying, yeah, there's a few molecules out there. That's not what I mean. Even if those few molecules weren't there, even if space was an absolute perfect vacuum, it would still not really be empty. Think about gravity. Back when we learned about gravity, were any of you bothered by the fact that, here's the Earth. Can you guys see? Okay, good. You see my little arrow moving around. Okay, so here's the Earth. Here's some other object. Looks like a baseball here, but let's pretend it's the moon. Okay, how is it that the Earth can somehow reach out with invisible fingers and grab the moon and pull it towards it? How is that possible? And that really should bother you. If that doesn't bother you, then I'm really worried. It should bother you. Now, I remember when I was a high school student, it really bothered me. Now, if the Earth had repelled the moon, I could understand that. Let me. Okay, so assume that I am the Earth. Okay, and so here I am, and if I throw this ball, okay, the fact that I throw it, it causes me to go back the other way, right? So when I throw the ball, I end up going back the other way. So if I was playing catch, if I'm on the Earth and I'm playing catch with somebody on the moon, I throw the ball to them, which makes me get pushed away. And then they throw the ball back to me, which makes them get pushed away. And then I catch the ball and that makes me get pushed away. So if I was playing catch with somebody on the moon, I could understand how the Earth and the moon could repel each other. But they're not repelling each other. They're attracting each other. How in the world could we throw a ball back and forth and end up with the net effect being that we're attracting each other? That boggles the mind. And they really, really bothered me, and I hope it bothers you. So if we're trying to explain how it is that the Earth can reach out with invisible fingers and pull the moon in, as opposed to pushing it apart, that should be a conundrum. And by the way, the same thing happens with plus charges, where with charges, if you have a plus and a minus, now the picture that you see, they're both pluses, so they would repel each other. But if one was plus and one was minus, they would attract each other and would have the exact same thing, the same problem. How does this charge reach out with invisible fingers, grab the other one and pull it towards it? Well, the answer is empty space isn't empty. You guys have probably seen pictures like this before, okay? What it's intended to illustrate is that there is something that surrounds us, that even if space was an absolute perfect vacuum, there is something there. So some people, they used to call it ether, but the term ether fell out of favor for a lot of reasons that I don't want to go into right now. So the current term that scientists use for it is the fabric of the universe, or some people call it the fabric of the cosmos. So the picture that you see here is meant to illustrate the fact that the Earth is somehow connected to this fabric. And the more mass the Earth has, the more it stretches the fabric. Okay, so the Earth is connected to this fabric. Now, this fabric, you can wave your hand all you want and you don't feel it, but there is, in fact, something there. So if the moon comes along, okay, the moon is also connected to the fabric, but look at the fabric around the moon. What you see is the fabric over on this side of the moon is stretched more tightly, and the fabric on this side of the moon is stretched less tightly. Okay, and so the moon, which is connected to this fabric, and it's got more tightness on this side, less tightness on that side. That the fabric is what is pulling the moon toward the Earth. Okay, it's the distortion in the fabric of the universe. So it's the same thing with electricity. If you've got a plus charge and a minus charge, okay, they distort the fabric. Now, the difference with electricity is that with mass, at least as far as we know right now, mass can only distort the fabric one way. So think of it. So here's a piece of fabric. Okay. All right. So with mass can stretch the fabric tighter, okay, which causes the moon to get pulled into it. Well, electricity can do the same thing. It can stretch the fabric so it's tighter, but it can also do the opposite. It can also expand the fabric, so that if I have a positive charge here, which is expanding the fabric around it, and a positive charge here, which is also expanding the fabric around it, those two guys are going to feel a repulsive force. Whereas if one is positive, one's negative, then they're going to feel an attractive force. Okay. So as far as we know right now, gravity only seems to work one way. It's attractive only. There are people who think that maybe there is some kind of, now I'm going to use the word antimatter, but be careful. antimatter does not mean that it has negative gravity. Antimatter means something else. We're going to talk about that later. But so some people think that there might possibly be some anti-gravity, that we just haven't ever found the right particles. But as far as we know right now, gravity only works one way, and electricity works in a very, very similar way. In fact, very identical, except for the fact that electricity can sometimes not only stretch the fabric more tightly, but it can also push the fabric out. Okay, and so because they work on through the same mechanism, that's why you see that the equation there is the same equation. The only difference is the magnitude of the constant. And that's worth talking about. Remember the magnitude of G? Can somebody please type into the chat box, what is the value of G? It's what times what to the what? Or what times 10 to the what? Somebody type that in. Okay, so 6 times 10 to the negative 11. 6.67 times 10 to the 11, negative 11. What about the value of K? Can somebody please type in what is the value of K? Okay, 9 times 10 to the 9th. Look at those two numbers. Okay, thanks. Good. We got it. Look at those two numbers. One of them is something times 10 to the negative 11. The other one is something times 10 to the positive 9. That's a huge difference in value. So it turns out that the electric force is way, 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 way more powerful than the mass. So think about a proton and an electron. Okay, so if you got a proton right here, and here's the electron that's orbiting around it, okay, they both have mass, and therefore they should be attracted due to gravity, and they are, but you don't have to worry about it. When you're doing the calculations in Mr. Miller's class to figure things out in chemistry, you can ignore gravity completely, because the electric force that's on these guys is 10 to the 20th times greater than the mass, the gravitational force. So when we're working problems with electrons and neutrons and protons and things, we can safely ignore gravity completely, because compared to the force of the electric, it's absolutely nothing. Okay, that's pretty much all that I intend to do with chapter 20. So we're going to move into chapter 21, and these fields that we're talking about here, they are exactly related to this stretching of the fabric idea. The Earth has a gravitational field that surrounds it, which, when we talk about gravitational field, what we really mean is how tightly is the fabric of the universe stretched. If so, down in the well here, where it's stretched a lot, we say the gravitational field is really strong. The further out you go, the weaker the field gets. And when you get out here really, really far, the field is so close to zero that we can basically call it zero. So this field that we're talking about here, electric fields, what we mean is how tightly is the fabric of the universe stretched. Now, right now, it looks as if there are two separate fabrics. There's one fabric which is affected by mass, and we call it the gravitational fabric. There's another fabric which is not really affected by mass, and as far as we can tell, it's affected by whether or not you have an unbalanced charge. So they look like they're two separate fabrics, but scientists suspect that they might actually be the same fabric. We just don't know enough about physics yet. And we have some precedent for this. It wasn't that long ago the scientists thought there were actually three fabrics. They thought there was the mass fabric, there was electric fabric, and then there was magnetic fabric, because it looked like the electricity and magnetism, they behaved kind of similar, but not the same. And so scientists thought they were two separate fabrics. But it wasn't that long. Okay, somebody drawing on my screen here. Okay. So anyway, it wasn't that long ago that they thought that electricity and magnetism were two separate things. But then the more we learned about electricity and magnetism, we eventually came to find out that they are in fact the exact same fabric. They just were looking at them in different ways. And so scientists suspect that the same might be true with gravity. Have any of you heard something called the grand unified theory? That's what scientists are searching for, is one theory that explains everything. And we find out that there's really just one fabric. We're just looking at it in different directions. But from now on, or for right now, we're gonna talk about the electric fabric as if it is a separate fabric from gravity. Okay, so electric field strength. So this equal sign here, if I had drawn it myself rather than copying it out of the book, I would have put 3 horizontal lines there, because I would say that the electric field strength is defined as the electric force on some particle divided by the charge on that particle. Okay, so this is the definition that we're going to use in most of your homework problems. This equation is really all you need to know. So if I want to know how tightly the fabric of the universe is stretched due to some object, all I need to know is what is the charge on that one object. I don't have to worry about what is the charge on of the other object, because remember, you have to have 2 objects, right? So I don't want to have the charge of the other object even enter into the equation. So what I do is I say, well, okay, I'll just assume that this other object here is a 1 Coulomb object. That way I'm dividing by 1. Okay, so all I have to do to calculate the electric field strength is just calculate what the electric force would be if it was a 1 Coulomb object. Okay, so in your homework tonight, you're going to have this. Now, if we want to picture what the electric field looks like, here's the rule. We are going to assume that this second object, which is sometimes called the test charge, we're going to assume that it's positive. So what we want to know is, what is the force if it was a positive object? So if we are anywhere near some other object, if that object is a positive charge, then the force on our test object is always going to be away from it. So what we do then is we say the electric field lines point away from an object if that object is positively charged. If, on the other hand, the object is negatively charged, then we say that the electric field lines point towards it. Okay, so in your homework, if they ask you to draw the electric field lines, well, just this is how it works. Now, if you have 2 objects, or 3 objects in this case, the electric field lines get really weird, okay? They always come out of positive objects, and they always go into negative objects. And if you have them, a weird arrangement like this, the electric field lines can be very, very difficult to predict what they're going to look like. If we only had 2 objects, then it's a lot more simple. What you're seeing here is we have 2 objects. Now we're assuming that they have opposite charge. Now in your book here, which that's where I got this from, I copied this out of the book, they didn't show which one is positive and which one's negative. So we don't know which way the arrows are going. So if the one on the left was positive, then the arrows would be coming out of it. And if the one on the right is negative, then it'd be coming out of the one on the left and then going into the one on the right. So you see the way that I'm tracing my little arrow here, okay, that's if we were to draw arrows on here, they would be pointing from the left one to the right one. Now over here on the left, this is what it would look like if both of the objects have the same charge. Now, if they were both positive charges, I would put little arrowheads on here showing that the arrows are coming out of both objects. If, on the other hand, they were both negative, then I would put the arrowheads on there showing that they're going into both objects. But the important thing here is you see that the lines do not connect up, whereas over on the left side, the lines do connect up. Okay, any questions so far? We're good? I'm going to keep going unless I hear somebody say nay or anybody ask a question. Okay, so in your homework tonight, you're going to have problems kind of like this. So this is example problem number 1 in the book. So they're saying that we've got a positive chest charge. So what that means is that's not the thing that's causing the field. So let's say this Q right here, well, okay, so this is a test charge. Somewhere else not shown in the picture is a bigger charge, and that bigger charge is what's causing the electric field. And so we're taking a little positive test charge and we're putting it here, and we want to use it to know how strong is the field. Now, you cannot measure fields directly. The only thing you can measure directly is a force. So what we're going to do is we're going to take this little test charge, and when we put it at this particular place, we notice that it has a force on it. And the force on it is 0.12 newtons, and the direction of the force is at an angle of 15 degrees north to east. Okay, so we want to know, okay, given that, what is the magnitude of the electric field? Not the force, but the field. Well, remember the definition of field. The electric field is defined as the force divided by the charge, the amount of charge that's on the little test sphere that we're using. So this little test sphere has a charge of 3 microcoulombs. So all I have to do is take the force and divide it by 3 microcoulombs, and that'll tell us what the field is. Now, the direction of the force is always, always, always the same as the direction of the field. Okay, so whatever the force is, the field is going to have the exact same direction. Okay, that clear? Let's type a few things in here. I'm always worried that the mic may have gotten turned off or what. Okay, do not fret. Okay, good. All right, so Josh is asking what's the unit on the field, okay? All right, well, Josh, if the definition of field is force divided by charge, what are the units on force? Newtons. What are the units on charge? Coulombs. So that means that the units for the electric field are always going to be newtons per coulomb. Okay. All right, here's another example. We want to know what is the field strength. And again, it's pretty much the same thing. I don't think there's much value in me going over it. These example problems that they have in the book are a lot more important now. Now that you guys are doing everything online here, it's really important that you work through every example problem in the book. I think they do a good job of illustrating what's going on here. So they state the problem, they show the picture, they show the steps to go through, show the answer. So as long as you guys work through the example problems in the book, you should be fine. So that's pretty much it. We've been going for almost 50 minutes now. So my goal is to try and keep these online lecture sections less than an hour. I cannot promise that I will always meet that goal, but that is the goal that I am going to try for most of the time. So it's about right. Okay, so your homework for today will be to take the daily quiz. So I'm going to do the same thing every time that we have an online class. I'm going to post the recorded session as part of the quiz. So so it's exactly the same way as last time. You know, when you go to the thing that'll be labeled quiz and recorded session, when you open it up at the top, there will be the video, which you are free to watch if you want, or if you don't need to watch it because you participated live, then fine, you can skip right through that. Down at the bottom will be the quiz. Now, it's my intention that the daily quiz questions will be really simple, because the homework is really where I want you to put your thought and effort. So the quiz questions will be really, really simple. You know, like for instance, you know, what color shirt am I wearing? Or a couple of really simple things. So don't fret the daily quiz. The homework problems, those are the important things. That's where I want you to spend your time and effort. The quiz and the homework, I'm going to make them both due by the beginning of class next time we meet. So as long as you post your answers by the time the class starts on Friday, they will be considered on time. But if you wait until after class starts, they will be late. Now, everybody does have 2 late passes, just like before, but you don't want to go using them up. Okay, so Yazin has noted that my hair is combed to his right. which would, I guess, be your left. That's a good one. Maybe I'll make that be the quiz question. I like that. Okay. Or maybe what I'll do is I'll have a secret word, and then I'll ask you what is the secret word. So somebody want to suggest a secret word for today? Lasagna. I like that. Okay. Grand. That's good too. Okay. Oh my goodness. Bazinga, quarantine, requiem. Okay. All of those are good ones. So one of those might be the secret word for today. So that might be the answer to a quiz question. You never know. Wink, wink, nudge, nudge. Okay. So I'm thinking, okay, so what time should you expect, the quiz to be up? Okay. The people at Zoom, it takes them about 1 hour or so to process the recording and make it available to me. And then it takes me a little bit of time to get that up. So usually you can expect about 2 hours after we finish the meeting here. That's when the daily quiz and the recorded session should be up. That'll vary a little bit. Okay, so Ellie is asking, can you retake the quizzes past the deadline if you originally did it on time? Yeah, I will allow that. Okay, so everybody understand that. So the daily quiz, if you didn't get a good score on it, you can retake it. But the daily quiz is going to be a lot easier than the quizzes we've done before. So hopefully that shouldn't be necessary. All right, so any more questions before I stop the recording and close the meeting? Going once. Will I have a nice day? I guess we'll find out. It's been kind of nice working from home. It has its positives. Okay, well, with that being said, okay, so I'm going to go ahead and stop the recording.